Integrating an external enterprise service like the Visma Sign API directly into a localized Google Workspace environment requires creating a bridge between two heavily guarded systems. The scale of vulnerability expands significantly when external applications request access to these ecosystems. Every open connection introduces a new vector for data exposure. Sign Goodi Flow addresses this specific workflow. Built on a React 19 and Firebase E2 stack, it manages document signing requests for organizations operating within Google Workspace. This image displays the Google OAuth consent screen for the application. It requests 8 distinct permissions, highlighting a volume of access that includes sensitive scopes like Google Drive and the organization's user directory. Requesting 8 separate, highly sensitive scopes guarantees intense scrutiny from technical reviewers and trust and safety teams. On paper, it looks like an application demanding unrestricted access to an organization's core files and contacts, but an expansive consent screen presents a theoretical risk, not an operational one, provided the underlying architecture enforces strictly bounded data flows. System compliance relies on physically and logically neutralizing the application's ability to overreach, ensuring the code itself cannot exploit the broad permissions it requires to function. The system starts with a standard identity and authentication layer. The OpenID, profile, and email scopes establish the secure user session, confirming who is initiating the signing request. This triggers a precise token exchange. The system takes the Google OAuth 2.0 credential, converts it into a Firebase custom token, and passes it securely into Firebase Auth to lock in the backend session. This diagram maps the application architecture. The application requests the broad Drive scope, opening a wide data pipe from Google Drive to the front end, yet the app only requires a single document at a time. The application introduces its primary structural boundary here. The custom file browser UI acts as a hard filter. When a user clicks a file, the application extracts only that explicit file ID and sends it to the backend. If that isolated ID points to a Google Doc, sheet, or slide, an automated pipeline immediately fetches the file and converts it into a static PDF, standardizing it for the Visma Sign API. The backend code is structurally incapable of scanning, indexing, or reading the wider Drive repository. Anything outside that single user-selected file ID remains entirely untouched. Once the Visma Sign process is complete, the system uses that exact same isolated scope to route the final signed document back to a specific folder in the user's drive. The risk associated with the broad Drive scope is neutralized because the broad permission of the API is entirely decoupled from the extremely narrow, file-specific execution logic of the application. Sending a document requires adding signers, which introduces a user experience problem. Manual data entry creates friction, and users need to add colleagues quickly without typing out full email addresses. The application solves this by requesting 2 specific read-only scopes, Google Contacts and the Workspace directory. This split view diagram shows the trigger mechanism. The moment a user types a keystroke into the React UI, a real-time API request fires off to the Google Contacts and directory silos to fetch suggestions. The extraction payload applies a strict filter. From the highly detailed directory data returned by the API, the application isolates and retrieves only 2 data points, the contact's name and their email address. Sign Goodi Flow operates on an ephemeral data architecture. As we see the Firestore database enter the diagram, a hard barrier guarantees this extracted contact data is never written to backend storage. The name and email data exist entirely in transit, populating the drop-down menu directly from the client's local memory. By discarding the data the moment the user closes the window or completes the selection, the organization's entire address book remains completely isolated from the signing application's database. Ephemerality allows the system to utilize rich, data-heavy UI features like autosuggest while maintaining a zero-storage attack surface. The system offers an alternative integration path, a Google Workspace add-on that executes natively inside a sidebar while a user edits a document. A standalone web app requires broad scopes to search for and fetch external files, but an integrated sidebar lives inside the host, allowing for a highly restricted access model. This visual maps the add-on architecture. The application uses the documents.current-only scope to establish contextual isolation. The sidebar locks its access strictly to the active window, blinding itself to all other files. Paired with the Drive.file scope, the application secures the rights to read and export only the file currently open in the editor, passing it directly to the signing service. Because the application knows exactly which file the user intends to sign, contextual isolation completely eliminates the need to request the broader Drive scope or load a separate file browser. The add-on also employs the workspace.link preview scope, reading just enough metadata from a pasted Visma Sign URL to render a rich, real-time status card directly in the document. By shifting the application interface directly into the host environment, the system leverages the user's immediate context to drastically shrink its required security footprint. Pulling back, we can evaluate the complete Sign Goodi Flow ecosystem, from the React interface down through the Firebase backend. This map defines physical data residency. Cloud Run, the Firebase backend, and Firestore database are strictly locked within the EU, specifically Europe North 1 in Finland. Encrypted transport layers safeguard payloads traveling between the user, Google Workspace APIs, and Visma Sign API. Explicit file selection, ephemeral data handling, and contextual isolation do not operate independently. They function together as a unified defense mechanism. This precise architectural bounding satisfies strict constraints of the Google API Services user data policy, guaranteeing permissions are utilized solely for stated functions. The physical structure of the application natively blocks Google data from being used for advertising, profiling, or unauthorized background indexing. True enterprise API compliance is achieved by meticulously architecting the physical and logical constraints around the data itself.